In this video, we're going to look at free rotation, conformations, and drawing conformations using Newman projections. Free rotation is the rotation of one atom relative to the other along the axis of a single bond that connects them. Now, because a single bond will always be a sigma bond, this means that there is no change in the overlap between the orbitals that make up that bond. And because there's no change in the orbital overlap, there's no change in the bond strength. Because of free rotation, molecules are constantly changing shape. We can look at a 3D model of ethane, and we can see the free rotation occurring along the carbon-carbon bond. You can see that the molecule is constantly changing shape. The different shapes that a molecule can take on because of free rotation are called conformations. So here I have two conformations of ethane. You can see that the two models have the same atomic connections, right? We have two carbons bonded to one another, each carbon bonded to three hydrogens. But the two models have different shapes. They're different conformations of ethane. Now, there is no free rotation along double or triple bonds. And this is simply because if you try to rotate a double or triple bond, the pi bonds involved break. Remember that a pi bond is a side-by-side overlap of two p orbitals. And if you try to rotate the sigma bond between the two atoms, then the p orbitals no longer will overlap. And when the p orbitals don't overlap, that breaks the pi bond. In other words, it's not free. It would actually be breaking a bond to do that rotation, and that would cost energy. We can depict conformational information using Newman projections. A Newman projection is a drawing of the conformation along one single bond in a molecule. In a Newman projection, we rotate the molecule so as to look down the bond we want to represent. So you'll have one atom directly in front of and kind of hiding the atom behind it. The front atom of the bond we're looking down is represented by the intersection of the three groups that are actually attached to it. If you look at ethane, ethane has that carbon-carbon bond. And so if we're going to draw a Newman projection of ethane along that bond, we rotate so we are looking straight down the carbon-carbon bond. And you can see that the front carbon has three hydrogens attached to it. So we draw those out, and the point of intersection is the front carbon. It's kind of like a skeletal structure at that point. The atom in the back is drawn as a circle, and then the three groups that are attached to that atom are also drawn, connected to the circle. Don't extend those bonds all the way to the center. They only connect to the back atom, and that means you draw them just connected to the circle. So here's a Newman projection of ethane, and you can see that it actually very closely represents the 3D model if you look down the carbon-carbon bond. And it's important to recognize that the bond you're looking down is not drawn, right? It's implied, it's sort of obscured. Now, one way that conformational information can be conveyed is in terms of a dihedral angle. A dihedral angle is an angle between two planes defined by two sets of three atoms having two atoms in common. Everybody got that? Probably not. Well, that's the real definition. It is a cumbersome definition, and it actually can be simplified. If you look at a Newman projection, or if you're looking at a model where you're looking straight down a bond like this, the dihedral angle is simply the angle between two different bonds or two different groups, one on the front atom and one on the back atom. So if you look at our Newman projection of ethane, there's that hydrogen on the front carbon that's pointing straight up. Then if you go clockwise from there, there's another hydrogen on the back carbon kind of pointing at an angle, right? The angle between those two bonds or those two groups, that's a dihedral angle. And in this representation, that angle is actually 60 degrees. Now, if we rotate one of the atoms that we're looking at in the actual bond represented here, you can see that as I rotate it, some of the dihedral angles get smaller and some of them actually get bigger, right? They move in sort of triplicate because as you rotate one atom and it has three things attached to it, you're going to see sort of three pairs of dihedral angles changing. Now, if you think about it, even a simple molecule like ethane is going to have an infinite number of possible conformations. We can express that with dihedral angles. If you think about one hydrogen on the front carbon and another hydrogen on the back carbon and the angle between them, it can be any possible angle. It could be 0 degrees, it could be 40 degrees, it could be 23.579 degrees. There's an infinite number of possibilities. Now, there are two particular conformations that are quite useful: the staggered conformations and the eclipse conformations. These represent the two extremes in terms of dihedral angles. A staggered conformation is where you have all of the adjacent atoms or close by atoms separated by a dihedral angle of 60 degrees. So the Newman projection I have here, that is a staggered conformation. You can see that if you compare the angle, the dihedral angle between any kind of nearby hydrogen atoms, you have 60 degrees, and it's actually constant, right? It's 60 degrees everywhere. An eclipse conformation is when the dihedral angle for the nearby atoms is 0 degrees. And when we draw an eclipse conformation as a Newman projection, we tend to skew it a little bit. If you drew it perfectly, you actually wouldn't be able to see the atoms and the bonds in the back. So we draw it kind of distorted a little bit so that we can see everything in the back. And of course, it's called an eclipse conformation because that's kind of exactly what's happening, right? The atoms and the bonds on the front carbon are in fact eclipsing. They're hiding the atoms and the bonds on the back carbon. So we said that free rotation is called free rotation because it doesn't change the amount of overlap between the orbitals in the bond that's being rotated. So it's free in terms of bond energy. But it's not free in terms of total energy. Free rotation can actually cause changes in the total energy of a molecule due to various forms of strain. The first type of strain we're going to look at is torsional strain. Torsional strain is the energy of repulsion as one pair of electrons passes near another pair on an adjacent atom as the result of free rotation. So as I rotate this front atom, you can see that the three bonds, and remember bonds are pairs of electrons, the three bonds on the front will get closer and then farther and then closer and then farther away from the bonds on the back. As the electron pairs get closer, well, they're going to repel one another like charges repel, and that's torsional strain. Torsional strain will be maximized when those electron pairs are as close together as they can be. In other words, when the dihedral angles are 0 degrees, and that means in the eclipsed conformation. The eclipsed conformation is the least stable conformation with respect to torsional strain. And that means that the staggered conformation is going to be the most stable because that's where we have the maximum dihedral angles when you compare any two nearby atoms. Now for ethane, the difference in energy between a staggered conformation and an eclipsed conformation is about 2.9 kcals per mole, so around 3 really. And if you think about it, there are 3 pairs of electrons that are interacting with one another, right? So you can kind of think of it as 1 kcal per mole per pair of electrons that are kind of interfering with one another. Now, measurements of energy are not something you're really used to, right? We measure things all the time. We measure things like distances and volumes and weights and such, and we're really accustomed to those, but energy measurements, not so much. So what exactly is 2.9 kcals per mole? Well, if you think of a typical covalent bond, like a CH bond or a CC bond, the energy in a typical covalent bond is around 100 kcals per mole. So here we're talking about 3 kcals per mole. We're talking about 2 orders of magnitude less than a typical bond. And we know that covalent bonds aren't just breaking randomly at room temperature, right? 100 kcals per mole is a good bit of energy. 3 kcals per mole, not so much. And it turns out that there's plenty of energy, even at room temperature, to overcome this 3 kcal per mole energy barrier. And that means that ethane at room temperature is constantly changing shape. It is constantly rotating around. The next form of strain energy we're going to look at is steric strain. Steric strain is the energy of repulsion as one atom or group approaches another atom or group in space. Now, this technically has nothing to do with free rotation, but it can be a consequence of free rotation. Let's take a look at another molecule. Let's take a look at butane. If you look at butane, it actually has 3 carbon-carbon bonds, and that means that if we were going to look at the conformational changes involved, we could look at any of those 3 bonds, and in reality, all those bonds are rotating. We're going to look at the middle bond. We're going to look at the C2 to C3 carbon-carbon bond. When you do that, you can see that each carbon of that bond has one non-hydrogen attached to it, right? It's got a methyl group, actually. Now, as we rotate that carbon-carbon bond, those 2 methyl groups can get closer and farther apart. When those 2 large methyl groups get close in space, their electron clouds repel one another. That's steric strain. As those groups get closer, they repel one another and it pushes it back. If you want to compress those 2 methyl groups close, you have to apply energy. That's steric strain. So we know that torsional strain is minimized, actually 0, when you have a staggered conformation. Let's look at the staggered conformations that are possible for butane when looking down that C2-C3 bond. One possibility is to have the 2 methyl groups pointing in opposite directions. Now that's going to minimize the steric energy between those two methyl groups, right? They're pointing as far away from each other as possible. This is in fact called an anti-conformation. Anti simply means that the two groups are pointing in opposite directions, 180-degree dihedral angles. If we now rotate that front carbon clockwise 120 degrees, we're going to get to another staggered conformation. Anytime you're looking down a carbon-carbon bond in a molecule and you're looking at conformational changes, you can always go from one staggered conformation to another simply by rotating one of the atoms 120 degrees. So here we can see we have another staggered conformation, except now the methyl groups are closer together. The dihedral angle between those two methyl groups is now 60 degrees, and that causes steric strain. This is called a gauche conformation. Gauche simply refers to when two groups have a dihedral angle of 60 degrees separating them. If we then rotate that front carbon again 120 degrees clockwise, we get to another staggered conformation. And you can see again we have that gauche relationship between the two large methyl groups. So again we have steric strain here. Now these two gauche conformations are different from one another. They're very similar looking, but they do have the same energy because the relationships between those methyl groups is the same, right? It's a gauche conformation in each case. They have the same dihedral angle separating them, so they have the same amount of steric strain. And again, both are staggered conformations, so they both have zero torsional strain. Now, of course, steric strain can be exaggerated even more if you start looking at eclipse conformations. If we look at how rotating the front carbon relative to the back carbon affects energy, you can see sort of a sinusoidal pattern to this. The sinusoidal pattern is because of the torsional strain, right? As you compress those dihedral angles to zero, torsional strain goes through the roof, and as they go back to staggered conformations, it drops down. But you can see it's not a perfect sine wave, right? Some of the humps, some of the peaks are taller than the others. And that's because of steric strain. We can maximize the steric strain and torsional strain by creating an eclipse conformation where the two methyl groups are actually eclipsing one another, right? So we have maximum torsional strain, maximum steric strain of those two large groups. That means we have the highest energy conformation. We can minimize all the energies in the anti-conformation. The anti-conformation is staggered, so it has no torsional strain, and it minimizes the steric strain between those two large methyl groups. So there's one more form of strain energy we're going to look at, and it's called angle strain. Angle strain is a destabilizing energy caused by a deviation from an ideal bond angle. And yeah, that's probably as clear as mud. So we're going to kind of demonstrate this with some examples, and it'll make a lot of sense. Angle strain is also often referred to as ring strain because cyclic molecules are really the most common way of encountering angle strain. So let's take a look at the simplest possible ring, right? A three-membered ring, cyclopropane. You might remember from some geometry classes in your past that 3 points define a plane. So we have 3 carbon atoms in cyclopropane. And that means that cyclopropane is planar, at least the carbons are all coplanar. Cyclopropane essentially looks like a little equilateral triangle, right? So what is the internal angle in an equilateral triangle? It's 60 degrees. Now if you think about it, all the carbons in cyclopropane are sp3 hybrid atoms. And sp3 hybridization wants to have bond angles of 109.5. Now remember, we're talking about bond angles now, not dihedral angles. But yeah, an sp3 carbon wants bond angles of 109.5 degrees, and yet we've squashed them into these 60-degree bond angles. That is angle strain. The very nature of putting these 3 carbons into such a small ring distorts the bond angles from their ideal bond angle. The ideal bond angle for an sp3 carbon is 109.5 degrees. We've made them 60. And that is a massive deviation from 109.5 degrees. So cyclopropane has a tremendous amount of angle strain. Now, cyclopropane also has a lot of torsional strain. If I show you the 3D model and I rotate it here, if you look down any carbon-carbon bond, you can see we have complete eclipsing, don't we? See how those bonds on the back carbon are being eclipsed by the bonds on the front carbon? Yeah, that means you have maximum torsional strain. And there's really nothing that cyclopropane can do about it. The 3-membered ring just doesn't really have any appreciable free rotation. It's kind of locked into that planar geometry, and so it cannot relieve that torsional strain. And what that means is that cyclopropane and other 3-membered rings are actually really, really strained. They're actually quite high in energy relative to other molecules. Now, what causes angle strain is pretty straightforward. You simply have your orbitals not overlapping properly. Remember that bond strength is correlated to orbital overlap. Better overlap means a stronger bond. And when you have your atoms pointing in sort of the wrong directions, Rather than having proper end-to-end overlap to make a sigma bond, you have sort of a weird angled interaction, and you get less overlap, and therefore the bonds are weaker, and therefore the molecule is less stable. So let's look and see how things are different for cyclobutane. Cyclobutane, four-membered ring, you would think, okay, fine, it's a square. It has an internal angle of 90 degrees. Well, that's pretty much true, right? If the molecule were planar, absolutely, that internal angle would be 90 degrees. And again, these are sp3 carbons. They want to have bond angles of 109.5, so you're still looking at about 20 degrees off. Now, that's a lot better than what we saw with cyclopropane, but it's still pretty bad. And again, if you look at sort of the planar molecule and you rotate it so you look down any carbon-carbon bond, you can see that we have eclipsing, right? We have lots of torsional strain here. However, with cyclobutane, that four-membered ring is just big enough to have a little bit of flexibility. In other words, 3 points define a plane, but 4 points, that is 4 atoms, don't have to be coplanar. 3 of them have to be in the same plane, but the 4th atom could be outside of that plane, above or below it. And that means that cyclobutane can actually pucker. It can pucker out of planarity, and when it does that, it relieves some of that torsional strain along some of those carbon-carbon bonds. Now, it may not be obvious, but that puckering action is actually the result of free rotation, a very limited amount of free rotation. In these small rings, you don't have a lot of free rotation. If you try to rotate a carbon-carbon bond too much, it distorts the geometry and the other bonds in the molecule simply break. So we have a tiny, tiny little bit of free rotation, and that allows the molecule to flex a little bit and pucker into this slightly distorted shape, relieving at least some of that torsional strain. Things get a little more interesting when we look at cyclopentane. Now, you're probably not as familiar with this geometry, this sort of regular pentagon, but the internal angle of a regular pentagon is 108 degrees. And again, we have 5 sp3 hybridized carbons that want bond angles of 109.5. And that's almost perfect, right? 108 degree bond angle is almost 109.5 degree bond angle. It's only a degree and a half off. And that means that there is very, very little angle strain in a cyclopentane. Again, if you look at the planar conformation of cyclopentane, if you look down any carbon-carbon bond, you can see that it's eclipsing, right? So you have maximum torsional strain. But again, as these molecules get bigger and bigger, these rings get larger, they get more and more flexible, and they can pucker out of planarity more and more. Cyclopentane actually adopts something called an envelope conformation. Essentially, you have 4 atoms that are roughly coplanar, and then the 5th atom kind of buckles up or down. It's supposed to look like a mailing envelope. Now, when cyclopentane adopts that envelope conformation, again, it relieves a good bit of the torsional strain. You can see that the bonds aren't really fully eclipsed anymore. Cyclopentane is pretty stable, right? It has very little angle strain, and now you can see that it's able to relieve a good bit of the torsional strain as well. So what that means is that cyclopentanes are pretty easy to achieve, right? In nature, there's lots of 5-membered rings. There aren't that many 4-membered and 3-membered rings in nature because they're so strained. They're really hard to make. Where things get really, really interesting is when we start looking at cyclohexanes and 6-membered rings. So think about what the internal angle of a regular hexagon is going to be. It's going to be 120 degrees. And for the first time, we've kind of shot past the ideal bond angle, right? For those first 3 smaller rings, each time the bond angles were less than the ideal bond angle of 109.5. Now we've actually gone past it. We're greater than. Although it's not bad, right? We're only about 10 degrees off from the ideal bond angle of 109.5 degrees for these sp3 hybridized carbons. And again, if you look at the planar conformation of cyclohexane, you can see that every single carbon-carbon bond is eclipsing, so you have maximum torsional strain. Now, cyclohexane and other 6-membered rings are actually really special because they can adopt a special conformation called a chair conformation. If you take the planar molecule and you take one carbon atom and push it up, and then you take the furthest carbon atom away from that and push it down, that creates a chair conformation. And it's called a chair conformation because it kind of looks like a lounge chair or a beach chair, right? If you think about a beach chair, you have the seat that's sort of flat that you sit on, and then you have the headrest that's sort of angled up, and then you have that footrest that sort of dangles down. So 2 things happen when a 6-membered ring adopts a chair conformation. One, it does change the bond angles a little bit. That 120 degree internal angle for a regular hexagon is only true if the hexagon is planar. Once you distort it out of planarity, the bond angles do change. And it turns out that it's about 111 in the chair conformation. And 111 degrees is even closer to 109.5, right? So it's actually very, very close. So in a chair conformation, there's very, very little angle strain. The other thing that happens, if you look at a chair conformation and you look at any carbon-carbon bond, if you look down the actual bond axis, you'll see that in a chair conformation, you have perfectly staggered carbons. And that's true on every carbon-carbon bond in the ring. In other words, a chair conformation has no torsional strain. Now, there is a little bit of steric strain from the carbons. If you look, right, the other carbons of the ring actually kind of get close to one another, creating gauche interactions. But there's no torsional strain, and the angle strain is almost zero. So when we look at the different conformations of any molecule, we can see the different kinds of strain energy that are involved: torsional strain, steric strain, and angle strain. And if you know the kinds of strain that exist in a given conformation, it can tell you a lot about what the molecule really looks like, or what it normally looks like. Remember, the energy differences we're looking at here are pretty small. These molecules are constantly changing shape. If you can deduce which conformations are the most stable and the least stable, what that tells you is what the molecule is going to look like and what it's mostly not going to look like. If you have a bunch of molecules of ethane, at any point in time, most of them are going to be in a staggered conformation or something similar to a staggered conformation. Very few are going to be in an eclipse conformation because it's higher in energy and it's less likely to be in that higher energy conformation. The same thing is true for these ring systems, right? If you think of a six-membered ring, it's probably not going to exist very often in a planar conformation. Now, it's constantly changing, but if you were to look at it over time, a six-membered ring is going to spend very little time in a planar conformation, and it's going to spend a lot more time in that much more stable chair conformation.